Hello, this is Dr. Armand again, bringing you another exciting lecture on acids. Today we'll be talking about how do we calculate the pH of a acid that has more than one acidic proton. For example, hydrosulfuric acid, carbonic acid. These are called diprotic acids because they have two ionizable protons on them. So we'll be talking about that today. We'll also be talking about weak bases. How can we gauge the strength of a weak base both qualitatively and quantitatively? Qualitatively, by looking at the structure, can we compare weak bases? And I'll go over some of the rules for that today. And we'll look at calculating the pH of a weak base solution. So sit back, relax, and let the chemistry begin. So I like to call this part 3 of the lecture. And again, today we'll be talking about diprotic acids and weak bases. We'll get to weak bases in a second, but just to talk about very briefly the three classes of acids based on the ionizable protons. And these three classes of acids include, of course, monoprotic, one ionizable proton. For example, there's thousands of different types of monoprotic: HCl, CH3COH. A lot of different organic acids are monoprotic. HNO3, HClO4, etc. That's one class. We've already talked about how to calculate the pH of monoprotic acids. We also have diprotic. Diprotic means two ionizable protons. There's not as many for these, but there are a few: H2S, H2SO3, H2C2O4, H2CO3, etc. And then the last group is triprotic. Triprotic is three ionizable protons. Not many of these. We have, for example, the most common: phosphoric acid, phosphorus acid, ascorbic acid, vitamin C, which I don't know the formula right off the top of my head. These aren't as common. And when you understand how to calculate the pH of a diprotic acid, it's very similar for a triprotic acid as well. But these are the three classes of an acid based on the number of ionizable protons. And generally, these are protons attached to a very electronegative element. So before we begin, just to kind of recap on the topics we talked about last time, and here we want to identify out of all these acids which one is the stronger or the strongest acid. And what you'll notice in all of these is that the acidic proton is attached to an oxygen. That's the first thing you should realize in this. All of these acids, the H is attached to an oxygen. So there's no difference there. So let's move on to the next step. First step, what element is the acidic proton attached to? They're all the same. We can't make any distinction there. We go on to the second criteria. What's the second criteria? Do you know this? This is resonance. So which one of these have resonance in them where the reaction center is? And again, the reaction center is at OH bond. And so this has resonance. 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 And this has resonance. So they all have resonance, and they all have the same amount of resonance because they're all carboxylic groups. So we looked at the element attached to the acidic proton, all the same. They all have the same magnitude of resonance. The next step is we look for electron withdrawing groups. So which one of these have electron withdrawing groups on them? Let's see. Well, A doesn't, just a double bond, but that's not electron withdrawing. B does, an iodine. It's not a very strong one, but it's there. C doesn't. D does, a nitro group is an electron withdrawing group. E does, it has an iodine. F does, it has a methoxy group. And G does, it also has a methoxy group. So what we can do right now is we can get rid of two of these because they don't have electron withdrawing groups. So A and C will not be in the top contenders for the strongest acid. So now we need to look at the strength of the electron withdrawing group. And so out of all of these, first we need to look at the position. Because remember, like we said, the closer it is to the reaction center, the greater the effect or the magnitude of the electron withdrawing ability. So on that note, we can get rid of B because it's on carbon 3, the electron withdrawing group, and G is on carbon 3. So we can get rid of that one. Now we're down to 2. We're down to, or 3, D, E, and F. Now here we have to know which one is the strongest electron withdrawing group. Is it NO2, I, or OCH3? And if you listened to last week's lecture, you should know this. The answer is, what is that? That's correct. It's NO2. So the one with NO2 would have the strongest electron withdrawing ability based on what's shown here. And this would be the strongest acid shown. So that's the thought process you go into determining which acid is the strongest qualitatively. One other review question, this one's similar to what we'll be talking about today. We want to know which one of these compounds is the strongest base. So strongest base. And so for bases, it's a little bit different. First, you want to look at the hybridization of nitrogen atom if we're dealing with amines, and all of these are amines. First, we deal with hybridization. Then we look at what's called the inductive effect. For inductive effect, we're looking at electron donating groups. So which bases have electron donating groups on them? Not electron withdrawing. So for bases, you want electron donating because it's going to pump electron density back into that reaction center. Because the reaction center for a base is that lone pair on that nitrogen. Then if we can't distinguish, then we go to if there's resonance. We want less resonance. So we don't want something that has a lot of resonance. We want to keep that negative charge on that nitrogen. So let's take a look at all of these. So first off, what's the hybridization of this nitrogen atom? And that is correct. It is sp3. Let me write that better. Undo. That's still worse. We'll just write it sp3. So that nitrogen is sp3 hybridized because it has 3 electron groups around it. What about B? B is also sp3 hybridized. So is C, so is D, so is E, so is F. They all have sp3 hybridized nitrogen atoms. So we can't distinguish based on the hybridization. Now we go to the inductive effect. Which ones have electron donating groups on it? Well, methyl group is electron donating. It's going to pump electron density. That's going to pump electron density. This one, ethylamine, is going to pump electron density. These are also going to pump electron density. And the same for these. They're all going to pump electron density back into the reaction center. Now for E, this one will be pumping, but these two will be withdrawing. The same for this. These two will be pumping, and this one will be withdrawing. So based on these, since E and F have electron withdrawing groups in addition to electron donating groups, we can go ahead and negate E and F. We're just doing this for very simple systems. So now we have A, B, C, and D. We got to think which one of these would be pumping the most electron density back into that reaction center. And the answer is, hope you said it, C. Because C has those T-butyl groups. They're very bulky, lots of methyl groups on there, lots of donating of electron density back into the reaction center. And so C would be the strongest base. Again, this is, just an introduction to looking qualitatively at the strength of bases. When you go into organic chemistry, you'll learn a lot more in depth about it. Now bringing us to polyprotic acids. Again, polyprotic acids have more than one ionizable proton. So since it has more than one ionizable proton, it has more than one Ka. So for example, phosphoric acid, in the first step, we dissociate the first ionizable proton. Since it's the first proton, it's called Ka1. Then using the conjugate base of the ionizing the first proton, now it goes and it dissociates the second proton. So then we have Ka2. And then to do the third proton, we get Ka3. And notice that the Ka decreases as you start removing protons, because the second and third protons become harder to remove compared to the first. So usually Ka1 is the largest, followed by Ka2, and then of course Ka3 if it's triprotic. So for example, oxalic acid, Ka1 is 10 to the negative 2, Ka2 is 10 to the negative 5. Sulfurous acid, 10 to the negative 2, Ka2 is 10 to the negative 8. Phosphoric acid, 10 to the negative 3, 10 to the negative 8, 10 to the negative 13. So that third proton only comes off on very basic conditions. Arsenic acid, 10 to the negative 3, 10 to the negative 7, 10 to the negative 12. So what this is showing you is that as you start removing protons, they become harder and harder to remove, which is noted by the lower Ka value. Now, because Ka2 is so much smaller than Ka1, we can assume that all the protons are being produced in the first step. So the pH of the solution is dependent on the first step, not the second and third step. Now so again, let me repeat that. Since Ka2 is a lot smaller than Ka1, we can assume that all the dissociable protons, or excuse me, all the concentration of hydronium ions comes from the first dissociation step, because Ka1 is so much larger than Ka2. So we can then say that the pH is dependent on the first step, because 95, 99% of the hydronium ion concentration comes from the first step. So we can approximate the pH of a solution just by knowing the hydrogen ion concentration of the first step. That's number one. Number two, if the Ka is small, just like in weak acids, we can negate the minus X. And if we negate the minus X, that means that the initial concentration of H2A is approximately H2A. And therefore, as we'll see, Ka2 is going to be the approximate concentration, in this case, for a fully deprotonated diprotic acid. But again, you can only do this assumption based on the 5% rule. So we'll call it assumption number 2. So assumption number 2 would not work for oxalic acid or sulfurous acid, so because OKAs are very large, 10 to the negative 2. So if you were doing oxalic acid or sulfurous acid, you would have to use the quadratic equation, because those Kas are very large Kas. For phosphoric acid and arsenic acid, it depends, because it's 10 to the negative 3. It depends. If you have a very concentrated solution, you might get by without having to use the quadratic equation. But if it's a dilute solution, you probably have to use the quadratic equation for that. Now, starting with carbonic acid and hydrosulfuric acid, you can use the approximation, because those Kas are very small. Now, I want you to notice here, the Ka2 for hydrosulfuric acid is 10 to the negative 17. So what does that mean? That means that the pKa of this acid is 17. The pH scale goes up to what? 14. So hydrosulfuric acid is never going to get rid of its second proton. It's above the pH scale, pKa of 17. So the best you can do is to deprotonate the first proton in hydrosulfuric acid. And even that requires a pH of around 7 to 8, around 8 pH. So now we're going to look at some calculations involving diprotic acids. So here we want to calculate the equilibrium values of H2S, HS minus, and S2 minus, and find the pH of a 0.05 molar solution of H2S. It gives us the Ka1 and Ka2. So let's first write the first step, H2S plus H2O Oh, that's bad. Gives HS minus plus H3O plus. And this is Ka1, which equals concentration of HS minus times H3O plus over H2S. I know it's a little bit sloppy, but I'm freehanding this, so bear with me. So that's what Ka1 equals. And then we have the second step, and I'll draw it down here. HS minus plus H3O plus equals S2 minus, oh snap, made a boo-boo. It should be H2O, not H3O plus. And Ka2 that. Okay. So now what we're going to do is to determine the pH. We're going to do the ice table for the first step. Because remember, all the hydronium ion concentration comes from, we're approximating, comes from the first step. So we go initial change equilibrium. So this is 0.05, 0.05, 0, and 0. Now the change, just like we did with weak acids, minus X, plus X, plus X. At equilibrium, 0.05 minus X, plus X, plus X. Now since the Ka is very small, 10 to the negative 8, our concentration is 10 to the negative 2. That's over 1,000,000 times magnitude difference, or about 1,000,000 times magnitude difference between the Ka and the concentration. So rest assured that you can use the approximation. So we can get rid of this minus X. So then Ka, we can set up our Ka expression, 9e to the negative 8 equals X times X over 0.05. You do some simplification, X squared equals 4.5 e to the negative 9. Therefore, X equals 6.71 times 10 to the negative 5th. So that's X. Now X equals, so once it's defined the concentration of all species, so H2S we said was unchanged. And by the way, look at it, I mean, Oh, snap. Oh, snap. So let me write it down here. H2S. So H2S is 0.05 molar. Look at X. X is 10 to the negative fifth. 0.05 minus 1 times 10 to the negative fifth is still going to be 0.05. The HS minus concentration is 6.71 e to the negative 5, which also equals the hydronium ion concentration as well. All we're missing now is the fully deprotonated species. Now, if we want to calculate the pH, pH equals the negative log of 6.71 e to the negative fifth. Be about 4.17. Now, to get the concentration of the fully deprotonated species, remember that we say that the hydronium ion concentration comes from the first step. So from the first step, we know that HS minus and H3O plus are the same concentration. So those cross out. And what we have left is that Ka2 equals the concentration of the fully deprotonated species. So the concentration of S2 minus would just be Ka2, which is equal to 1 e to the negative 17. So you can see that 6.71 times 10 to the negative fifth plus 1 e to the negative 17 is still going to be 6.71 times 10 to the negative fifth. And so these are the concentrations of all species and the pH of this solution of 0.05 molar hydrosulfuric acid. So here it wants us to determine the pH and the fully deprotonated conjugate base of para-hydroxybenzoic acid. It's a 0.02 molar solution. And it gives us pKa1 and pKa2. So here we have hydroxybenzoic acid plus water gives us Ba minus plus, oh no, H2Ba, HBA minus plus H3O plus. This is the first step. This is Ka1. Ka2, HBA minus plus H2O gives Ba2 minus plus H3O plus. And this is Ka2. Now it gives us pKa, and we need to find Ka. So the way we go from pKa to Ka is Ka is equal to 10 raised to the negative pKa. So to find the Ka1 equals 10 raised to the negative 4.06, which equals 8.71 times e to the fifth, negative fifth. We do the same thing for Ka2. Ka2 equals 10 raised to the negative 9.92. Get 1.20 to the negative 10. So those are how you go from pKa to Ka. Now we have our Kas. To determine the pH, that's going to come from the Ka1 step in the dissociation. So we're going to be using our ice table. So initial change equilibrium. Different concentration is 0.02. Oops, 0 and 0. Change, of course, minus x plus x plus x. Equilibrium, 0.02 minus x plus x plus x. Now notice here, pay attention here, notice that the concentration is 0.02, 10 to the negative 2. The Ka1 is 10 to the negative 5th. So 10 to the negative 2 over 10 to the negative 5th, you're looking at 1,000 times magnitude difference between Ka and initial concentration. So we can negate the minus x. So then we get 8.71 e to the negative 5th equals x squared divided by 0.02. And then we get x squared equals 1.74 e to the negative 6. And then x equals 1.32 times 10 to the negative 3, which equals the hydronium ion concentration. So to calculate the pH, let's do it up here. pH equals a negative log of 1.32 e to the negative 3. Snapperoo. And this one, the percent dissociation is 6.6%, so you wouldn't have needed to use the quadratic equation. But let's just change it up a little bit so we don't have to, so we don't have to redo all of this. Okay. Instead of 0.02, let's make it 0.2. So we're going to do a 0.2 molar solution of, and the reason I'm changing is because when you have 0.02 molar, your 5% rule fails because you ionized 6.6%. So at equilibrium, now 10 to the negative 1 divided by 10 to the negative 5 is 10 to the 10,000 times difference between the two. So now we can for sure negate this minus x. And then we get 8.71 e to the negative 5th. equals x squared divided by 0.2. X squared equals 1.74, 10 to the negative fifth. And so x equals 4.17 e to the negative 3. And if you check this with your 5% rule, you'll see that it works. It's only about 2% ionized. So that's okay. And again, this equals the hydronium ion concentration. So now we can take the pH. So the pH equals 2.34. That's the pH. Now it wants to know what's the concentration of the fully deprotonated species. So now we're going to write the expression for Ka2. And so from step 1, we know that the concentration of H3O plus is equal to the concentration of HBA minus. And that's the first assumption we talked about on the previous slide. So we can negate these two. So therefore, the fully deprotonated species is 1.20 e to the negative 10. So these are the two answers to the question. So now we're talking about weak bases. So a Bronsted-Lowry base, remember, it accepts a proton. The base needs a accessible lone electron pair. Typically, if it's an amine, it's going to be the lone pair on the nitrogen atom. Or it could be, if it's a single bond oxygen with a negative charge, it could be a lone pair on the oxygen atom. And so it's very similar to weak acids. Again, we have a dissociation equation. But notice here it's the conjugate acid and the hydroxide ion concentration that are on top. And instead of Ka now, we use Kb, base dissociation constant. So if we know the Kb, we know the initial concentration of the base, we can determine the pH of the solution. We'll have to do one extra step because we calculate the hydroxide ion concentration. When we take the negative log of that, it's POH, and then we can subtract it from 14 to get the pH. And just like with pKa, pKb, you can find by taking the negative log of Kb. Two things that we're going to talk about in a second, but I'll go ahead and let you know, is Kw equals Ka times Kb. So if you don't know Ka and you know Kb, you can find it by using this equation. Also, pKa plus pKb equals 14. So if you know the pKa, you can find the pKb. And the stronger base has a higher hydroxide concentration, which means a larger Kb or lower pKb. And there are two classes of weak bases. The first one are molecular species such as ammonia and the amines. The second one is anions of weak acid. So if you have an anion of weak acid, it's a weak base. So to get the Kb of the anion of the weak acid, you have to take the Kw divided by Ka. So again, to get the Kb, equals Kw divided by Ka of the weak acid. That's how you find the Kb of most anions of weak acid. Because if you look in the back of the book, there's no Kb for example, acetate. You take the Kw over Ka to get Kb. So again, you have to have a readily accessible lone pair of electrons. The nitrogen, for example, is electron rich. The hydrogen is electron poor, is looking for negative charge. So it gets attracted to that lone pair. It pulls the hydrogen, bonds to the hydrogen. So it accepts a proton. As you can see here, and this is very important here, pay attention. You see that diethylamine is more basic than dimethylamine. And let's take a look at that. Because they both, and even methylamine, let's look at these, and ammonia. So ammonia, methylamine, dimethylamine, and diethylamine have what type of hybridization? And you should know this. 4 electron pairs is going to have sp3 hybridized. So all of these are sp3 hybridized. Okay? Now the difference between ammonia, methylamine, dimethylamine, diethylamine is that we're adding more what? More alkyl groups. Alkyl groups are electron donating groups. They're going to pump more electron density into that nitrogen, making it more negative. So that's why diethylamine has a higher pKb, or excuse me, a lower pKb than dimethylamine. And then you look at pyridine. The nitrogen in pyridine is what hybridization? sp2. So since it's sp2, it's going to be a weaker base than sp3. Now you may ask, aniline, this nitrogen is sp3, but it has a lower pKb than pyridine. And the reason is because this nitrogen, there's resonance that the double bond can resonate onto the nitrogen. Since the double bond can resonate onto the nitrogen, it makes it less basic. So 2 classes of weak bases, amines or ammonia, and anions of weak acids. Remember that, that's very important. So weak bases. So like I said, to get the Kb, sometimes Ka times Kb equals Kw. So here we have an example of a weak base. Amphetamine, which is a weak base, just like acetaminophen, which is a weak base. Weak bases are good because they can cross the blood-brain barrier very easily, weak bases. That's why some of your like nicotine, amphetamine, acetaminophen. Oh, what else? Caffeine, caffeine, nicotine, amphetamine. There are amines. They can cross the blood-brain barrier. That's where you get this kind of, I guess, feeling of euphoria, is a way to put it. And so we want to know what's the pH of a 0.075 molar solution of amphetamine. And it gives us the Kb. So here we have, and I'll do an abbreviation, we have amphetamine plus water gives us the conjugate acid plus OH minus. Notice here that the Kb is a lot smaller than the initial concentration, and for most weak bases, the initial concentration is going to be a lot larger than the Kb, so most of the time you can do the approximation. So now we look, we have the initial, change, equilibrium. Oh snap. So the initial concentration, 0.075. For the products, of course, 0 and 0. The change, minus x, plus x, plus x. Everything's the same that we've been doing. So it'd be 0.075 minus x, plus x, plus x. Now notice here the Kb is a lot smaller than the initial concentration, so we can negate this minus x, and then we get 6.3 e to the negative 5 equals x squared divided by 0.075. X squared equals 4.6. X equals 2.17 e to the negative 3, which equals hydroxide ion concentration. So now we can find the POH, negative log of 2.17 e to the negative 3. .66, but don't forget at this step, this is the POH. It asks for the pH. So then we got to subtract it from what? 14. And that would be, what is that, 11.34, right? Yeah, that's right. Yeah, and that's the pH of this solution. So it's very basic. So again, don't forget that when you find X, you're finding then the POH, and then you convert it to pH. Now here's one involving an anion of a weak acid. So we have sodium hypochlorite, an active ingredient in bleach. What is the pH of a 0.2 molar solution of sodium hypochlorite? It gives us the Ka of the weak acid of the anion. So again, sodium hypochlorite, the sodium, it doesn't have to be sodium. It can be potassium, lithium, it doesn't matter. You're just going to disregard the metal. You're only interested in the anion. So what we have here, we have hypochlorite, and we'll learn next lecture why sodium doesn't affect pH. And this is the dissociation. This equals Kb. Now what we have is Ka. So define Kb. Kb equals Kw, 1 e to the negative 14 divided by the Ka, 2.9 e to the negative 8. So KB equals 3.45 e to the negative 7. Now we have the KB, we can do the same jazz we did before. So again, initial, change, equilibrium. So initial, 0.2 for hypochlorite. 0 and 0. Change, minus x, plus x, plus x. Equilibrium, 0.20 minus x, plus x, plus x. Now notice here, concentration 10 to the negative 1, KB 10 to the negative 7. That's like what? Factor of 6 difference between the KB and the initial concentration, so we can negate this minus x. Bada bing. And now we have 3.45 e to the negative 7 equals x squared divided by 0.20. X squared equals 6.9 e to the negative 8. X equals 2.63 e to the negative 4, and this also equals hydroxide concentration. And so the POH equals a negative log .58. And then remember, don't forget to find the pH. pH is 14 minus 3.58, which would be what? 10.42. And that's the pH of the solution. So again, make sure when you find X is the hydroxide ion concentration. You find the POH and then you subtract it from 14 to find the pH. So on that note, that concludes today's lecture over calculating the pH of diprotic acids or polyprotic acids and also weak bases. Again, I recommend that you watch this more than once. You watch it once, you take notes. You watch it a second and third time, try to work out the problems by pausing the video, work it out, and then checking your work. I strongly recommend you watch this multiple times. That way you can grasp the information. So again, as you work through it, you pause it, do the work, and then check your work. Listen to my explanation. And that'll help you in the long run prepare for these topics. So on that note, the next lecture will be about how can we determine the pH of salt solutions. So if we have, how will we know that sodium chloride solution is neutral versus potassium nitrite solution is slightly basic, whereas ammonium chloride solution is slightly acidic. So the next lecture will be talking about the acidity and basicity and neutral salt solutions. So on that note, that's Dr. Armand signing off until next time. So have a good day.